Our participant numbers seem to have stabilized, so I think we can make a start. Welcome everyone to the August edition of our Matrix Online seminar. Before I introduce the speaker, just some housekeeping things. So as usual, the seminar will be about 45 minutes in length, and after that, Ole will answer questions. So if you have any questions, either after the seminar or during the seminar, please watch those through the Q&A button. The chat button won't be looked at, so please use the Q&A button, and then at the end, Ole will try to answer as many questions as possible. So also I'd like to draw your attention to our September seminar, which is given by Professor A.V. Wicherton from the Institute for Advanced Study at Princeton, who is the 2021 Abel Prize winner, so that would be a very interesting seminar. And furthermore, I'd like to draw your attention to a set of math documentaries we'll be showing during National Science Week. We're showing 4 math documentaries during the period 16th to the 18th of August. 3 of those are directed by a Russian director, Ekaterina Eremenko, and she'll be present after the showing of the documentaries for question and answer sessions. Okay, so much for the housekeeping. So it's a pleasure to welcome Ole Warnaar as our next Matrix Online seminar speaker. So I've known Ole for a long time. Ole grew up and studied in the Netherlands, where I'm from as well. He studied in Leiden and did his PhD in Amsterdam, and then moved to Australia in 1993 to take up a postdoc at Melbourne University. And then after a brief interlude back in Holland, he settled permanently in Australia in, let me check my notes, in 2000, where he was at the University of Melbourne and moved to a chair at the University of Queensland in 2008. And he's still in Queensland, at home at the moment, I think. So Ole, well, he has many accolades to his name. He was made a fellow of the Australian Academy and in 2008. And he won the George Zacharias Medal, which is the most prestigious medal of the Australian Math Society, jointly last year. He's currently part of our Matrix Advisory Board and also the president of the Australian Math Society. So his research interests cover a wide range of subjects, from algebraic combinatorics to number theory, special functions, and representation theory. And today he'll be talking about plane partitions. Welcome, Ole.
Thanks very much, Peter. Okay, let me start sharing my screen. Okay, is that visible for everyone?
Yeah, that's good.
Okay, well, thanks very much for giving me the opportunity to speak. So today I'll try to tell a bit of a story about plane partitions. And well, my plan is to do this in a sort of colloquium style. So there certainly will be a bit of background and history to the subject, and then hopefully, if time permits, I know there's only 45 minutes, I'll talk about some more recent things that I've been working on related to plane partitions. Okay, so let's start. So before I can start talking about plane partitions, I should probably briefly remind everyone what an ordinary or integer partition is. So that's, to me, that's just a weakly decreasing sequence of positive integers that sum up to a given number, let's say n, and then we say we have a partition of n. And so, for example, the sequence 5, 3, 2, 2, 1, so that's my example here, that would be a partition of 13, because if you add up these numbers, then hopefully I didn't make a mistake, and 13 is what you get. And one can also represent a partition just using a diagram where we essentially just stack unit squares. And we do this in a weakly decreasing fashion. So the 5 in my partition, that would just be a row of 5 squares, and then below that a row of 3 squares, and so on. And I like it to be unit squares, so that really the size of the partition, so the number being partitioned, is exactly the same as just the total area of the diagram that's shown here. Okay, so that's integer partitions. So that's really an ancient subject. So essentially Euler was the first to really take an interest in these objects and study them quite extensively. And he's got many results on integer partitions, and one of the most important ones, it's not very deep, but it's important nonetheless, is that he gave a closed form expression for the generating function of integer partitions. So if we sum over all partitions and we measure this absolute value around lambda, that's just again the size or the number being partitioned. And I also keep track, for example, of the maximum part in the partition. So if I go back to my previous slide here, so 5 would be the maximum of that example of the partition of 13. And it turns out that you get a nice product formula on the right-hand side for that generating function. Okay, so that was Euler. This was not quite Euler, but it will be convenient for us later to have a slightly different view of an integer partition in terms of just a lattice path. So what am I going to do? I just draw a grid here, essentially of width A and height B, and I consider a dig path. So what I can do is I can take a step to the right or I can take a step upwards. So can everyone see my cursor? I'm not sure if that's sharing as well. Anyway, so for example, I start at the origin, I take 2 steps to the right, then 1 step up, 2 steps to the right, and so on, till I end up in the point A, B. And I measure the height of all of the horizontal steps, and that gives me a weight of that particular path. So in this example, the first 2 steps, they're at height 0, so they don't really contribute, and 2 at height 1, and so on. And of course, again, this gives you exactly that same 13 as before. You can recognize I've sort of colored this in light red or pink, perhaps. It's the same diagram of the partition, just rotated by 180 degrees. And well, we can take this, so the generating function of all paths starting at the origin and ending at AB. It is one of the definitions one can take of what's known as the Q-binomial coefficient. So of course, we all know that if we take the set of paths from the origin to AB, if we count the number, that's just the binomial coefficient. So here we have a weight related to this, again, the sum of the horizontal, or the positions of the horizontal steps. This gives you a Q analog of the binomial coefficient. So that's this Q binomial coefficient here. As I said, it's just the generating function of all of these lattice paths. And so it's immediate from this picture. That's of course the same as the generating function of all partitions, but now they are contained in a box of dimensions A times B. And so that still gives you a nice product formula, but of course it's no longer a Q series. This is now actually a polynomial in Q. Okay. All right, so I'm going to need this later when I start talking about plane partitions. So that's why I wanted to talk about these boxed integer partitions for a little bit. So let's now move to the actual topic of my talk, and that's plane partitions. So this was, well, probably 100 years after Euler. McMahon introduced essentially higher dimensional analogues of integer partitions. And by far the most important higher dimensional analog is that of plane partitions. So I'll mention briefly a little bit later some higher dimensional analogs, but the most important ones are the plane partitions. And essentially what we do is now we have an array of positive integers. So that's these, try to draw this here in a little diagram, these pi ij, they're all positive integers. And now we have weakly decreasing if you move to the right, but also weakly decreasing if you move down. And the length of the rows is also weakly decreasing. So the row length themselves, in fact, you can see that that's determined by some partition. And if we have R rows, that's determined by a partition of exactly R parts. And again, we can measure the size of such a plane partition by adding up all these positive integers. And so then we would have a plane partition, say, of the number n, if the sum of all the pi ij's is exactly n. Okay, so that's not very appealing to look at it this way. So let's just look at an example. So here, at the top of the page, you see an example of a plane partition. So we see all these numbers, and you can see that if you go to the right or if you go down, that you're weakly decreasing. And also you see that these row length are weakly decreasing if you go from top to bottom. And so this would be, again, if I haven't made a mistake in my arithmetic, this would be a plane partition of the number 30, because if you add up all these numbers, you get 30. But of course, more appealing still would be to just view this now as stacking of unit cubes rather than the unit squares that we had for ordinary partitions. And so now we stack these unit cubes and you get a picture such as you see at the bottom of the page. And I take unit cubes, so again, the size of the number being now plane partitioned, if you wish, is exactly the volume of this, this little object here. Okay, so that's a plane partition. And just like Euler did, you can ask yourself, well, can you enumerate these things? So can you compute, for example, the generating function of these objects in closed form? And well, you can. And so the simplest case, which is just the analog of the formula that we saw in the case of integer partitions. So now we take the generating function of plane partitions. So we again q to the size of the plane partition. So that's just the volume of that stacking of cubes, or just the sum of all the integers in this little diagram here. And rather than the max, so rather than the largest integer, there is some other quantity that we call the trace, which is essentially the sum over the diagonal entries. So, which is not something that was considered by McMahon, I should say, but much later Richard Stanley included the trace. So in the example here, the trace would be 4 and 3. That's what we have along the main diagonal. So that would be the trace would be 7, for example. And then we get, again, a nice product formula, very, very similar to what Euler had. And the only thing that really changes is that we now take nth powers in the denominator. And I should say that, because later I'll be returning to this max, that there is no simple closed form expression as a product if you try to enumerate plane partitions by size and by the maximum entry in that plane partition. So trace is really the good statistic here, not so much the maximum entry of your plane partition. Okay. Well, McMahon did a little bit more. So I mentioned earlier that, in fact, you can do this for any dimension. So I'm not going to formally define that for you, but you've seen the ordinary partitions, you've seen plane partitions. So it's obvious that you can do this in any dimension. And so McMahon considered the d-dimensional case as well, where d is 1 is just integer partitions and d is 2 it's the plane partitions. And he conjectured a closed form again for the generating function. But it turns out that this generated, his conjecture is actually wrong. And it took quite a long time, interestingly, for this to be shown. I believe that McMahon himself at some point no longer really believed in his conjecture. But it holds true, surprisingly, up to order q to the power 5 for any dimension. And so you really need to go quite high in order, or you need to already enumerate quite a lot of these higher dimensional partitions before you see a counterexample. So that was only shown in 67. And you might expect, well, by then we had computers and someone would just quickly have encoded this and just observe this. But these 4 authors that actually showed that McMahon's conjecture was wrong, they gave an algebraic proof. So they still didn't use computers to do this. Anyway, so for this reason, well, we now understand much better why sort of these higher dimensional partitions, they're not as interesting. It turns out that not many nice things happen. So there's not a lot of mathematical structure that you can develop that really explain what's going on. So most interest these days is certainly restricted to just the 2-dimensional case. Okay. So box plane partition. So as I mentioned earlier with integer partitions, if you can put it in a box, you get essentially that the generating function is given by Q binomial coefficient. So McMahon tried to do something similar for plane partitions. So again, he put this in a box, and so now, of course, we have 3 dimensions, sort of width. Well, I guess the A and B, that's sort of how you put it in the XY plane. And then we have the 3rd dimension C, that's sort of the height of the plane partition, if you wish. And so here I've shown you a picture of a plane partition in a box. And I've just chosen to tile or color also the walls of this box, so that an equivalent way to view this is actually as a tiling of this diagram here. So these are known as lozenge tilings. So these box plane partitions are equivalent to tiling problems. And again, it turns out that something really nice happens because McMahon was able to compute the generating function now for plane partitions contained in a box of dimensions A, B, and C. And he has well, I think this is certainly a very beautiful formula. It's I think it's one of my favorite formulas. It's not terribly deep, but it's very pretty, I think. And so, of course, this formula is nicely symmetric in A, B, and C, as it should be. So that was a result of McMahon, and I'll get back to that a little bit later, how you can prove this. As I said, it's not very difficult, but it's certainly a nice result in my opinion. But McMahon did more. He also considered, well, I should say there's on top of the ordinary partition, so there's a further 9 symmetry classes. So you can impose various symmetries on these plane partitions. Not all of them were considered by McMahon, but he certainly considered some. And it turns out that for all of these symmetry classes, so here I write 9 symmetry classes. Typically, if you look in the literature for plane partitions, people talk about the 10 symmetry classes for plane partitions, but that includes the plane partition case without symmetry. So that's one of the symmetry classes, is no symmetry. And so in any case, so on top of the no symmetry case, there's another 9 cases. And all of these, again, have nice closed form formulas. So McMahon himself, already very early on, found the closed form formula for the symmetric plane partitions. And so the symmetry here is, well, hopefully the picture shows, it's the symmetry in the sort of main diagonal of the plane partition. So the left and the right hand side of this picture look the same, which is also why there's no longer an A, B, and C, because B, without loss of generality, you can assume that A is equal to B, because it only depends on the minimum of the 2 if you have a symmetric picture. So here is a symmetric plane partition. And again, he found a nice product formula for the generating function. Now this, it's maybe not a priori clear, but this is much, much more difficult than the previous formula. So as I said, this is pretty, but not terribly deep. This is also pretty, but also deep. So in particular, it took about 75 years before this was proven. So that sort of goes to show that this is not an easy result. And it was independently proven, as often sort of happens in mathematics, of course. The problem is out there for a very long time. And then when it's finally proved, it's done by more than one person. So in this case, it was Ian MacDonald and George Andrews. Their proofs are very, very different. But it certainly took a long time. And for some of the other symmetry classes, it took even longer, although it also took much longer before they were actually formulated. So the last case, which is the totally symmetric plane partitions, that was only settled, well, it's now exactly 10 years ago. So again, that indicates that with the symmetry classes, things are becoming difficult. And in this last case, in fact, it's so difficult that the eventual proof that was published by Kutscher, Cowers, and Zalberger is very much a computer proof. So we don't really have a proof that explains what's going on, but these 3 people are very, very clever designing sort of these algorithmic ways of proving statements in mathematics, and that's what they did. And indeed, I mean, in their paper, they finish with an epilogue, and this is, I mean, I won't read it all out to you, but they certainly readily admit that their proof is not at all pretty, right? It's very heavily dependent on the computer. And of course, they speculate about proofs in the book, and maybe there isn't one, and maybe there is. But in any case, it certainly hasn't been found yet. So that again indicates how difficult some of these problems are. And on the left of this picture here, that's Doron Zalberger, and he has, so this was when they actually, so that, as I said, this was the last symmetry class to be settled. And because it was a sufficiently complicated problem, they in fact won the 2016 AMS David P. Robbins Prize. And this photo was taken at that AMS meeting where they received the prize, and Doron Zalberger has a t-shirt with the actual problem printed on his t-shirt. So you can see these numbers there. That's the generating function of these totally symmetric plane partitions. Okay, so in any case, so these symmetry classes are difficult. So, and I'll get back to that a little bit later, but let's first go back to the problem that was not so deep, and that's the one that was considered by McMahon, just the plane partitions in a box without any symmetry. And this is what I'm going to tell you here, certainly not what McMahon did, but it's a powerful approach to at least make some progress, not just for the non-symmetric case, but also for some of these symmetry classes. And so what you do is you reformulate the problem in terms of lattice path, just like we did with in the case of just integer partitions. So here on the left, it's my same example of a plane partition in a box. And what you do is you just draw these lines, you see that in the picture on the right, of lattice paths. So essentially you just start at the top and you just follow the profile of each of these slices. And then what you do, well, here you see that same picture that I have on the right extended again. I just make these lines a little bit longer at the top and the bottom. That's the bits you see in red. And then I just put this in a two-dimensional picture. And what we want the generating function, we want to keep track of the volume. So that's, of course, the height of each of the sort of columns in the picture on the left. And so I've just written that in the diagram on the right. That's these heights that you should be computing. But the way I've put this picture together on the right, you can see that some of these paths, so again, the left bottom corner, that would be the point 0, 0. The origin. So this rightmost path is indeed in the correct position, but the second path above it has been shifted up by 1, and then the path below, above, oops, that's no good. The path above that is again being shifted up by 1. So you need to, if you want to compute the generating function of these plane partitions in a box, you need to compensate for the fact that some of these paths have been shifted. So the first path is not shifted, the second one is shifted by just 1, and it has width b, so that gives you an extra q to the power b. The second path has been, again, has width b, but it's been shifted by 2, so it gets 2b, so you get this simple binomial coefficient that you need to compensate for. But after you've done that, all you need to do is just compute the generating function of these non-intersecting lattice paths, where these paths start at 0, 0, and then 1, 0, 2, 0, and so on. And they go up to the exactly, again, they separated by 1 at the top. So we just need to compute all configurations such as this. Again, compute the height of each of these horizontal, of all of the horizontal steps, and we're done. Now, of course, there's a problem here because these paths cannot intersect. And so it's not so easy combinatorially to compute all of these configurations. It would be much simpler if all the paths were allowed to intersect. So essentially these paths just become like solitons. They don't really care about each other. and you can just compute the generating function of each of the individual paths. So that's the trick. So what you do is you just throw in all paths that intersect as well, which of course you shouldn't have. And so now, because paths can intersect, so here I've just colored all of the different paths. Now, because the paths intersect, it's no longer true that the path that starts in the position 0, 0 will necessarily finish the first, and the second path is not necessarily finishing second, and so on. So to each of these pictures, there is a permutation attached, which essentially says, so here the permutation is 3, 2, 5, 7, 1, 4, 6. That's because the first path finishes in third position. The second path, this is the blue one, it finishes in second position, and so on. So that is just encoded in a permutation. And then there is something that is the sign of the permutation. You either know what the sign of a permutation is, but for us, it's good enough to just say it's the number of crossings in your picture. So if I did make a mistake again, then there's an even number of crossings in this picture. And so then the sign is 1. If there's an odd number of crossings, then the sign is -1. So what do we do? So we've thrown in all these additional paths, which of course we shouldn't have at all. But then there's this very simple involution principle. So what you do is you find the first crossing from the left. And if there's more than one in that first column, then you take the lowest one, for example. And all you do is you just switch that crossing around. So I've sort of put a little circle around that first crossing. And you can see in that picture on the right, I've destroyed one crossing. So I've changed the sign from a +1 in this case to a -1. But I haven't changed any of the heights of the horizontal steps. So these two configurations have the same horizontal steps, the same positions, so they have the same weight, but they have a different sign. So if we now add all these pictures, but we keep track of the sign, then all of the paths that intersect are just going to cancel out. So they won't contribute to the generating function. And then, and I apologize for the next slide, it has a sort of a lot of formulas in there, but that's the only slide of this kind. So now we can just compute the generating function of these box plane partitions. So the top line on the right just says, well, we need to compute the set of, or the generating function over all these non-intersecting lattice paths. That was difficult. So the second line says, well, we'll just throw in all paths. So now we, of course, have these paths that are, every path now is attached to a permutation. So we also need to sum over all permutations. And we need to keep track not just of the weight of the path, but also of its sign. And as we had seen, all the paths that have an intersection, they all cancel out pairwise. Well, and then in the next step, now because these paths are essentially like solitons, you can just compute its generating function for each of these paths. They don't care about the others. There's no longer any difficult combinatorics. And we saw earlier that a path from just a single path, dict path starting and ending in a given point was just given by a Q-binomial coefficient. So that's what we get here. And then finally, you can just write this as nicely as a determinant. So the generating function of these box plane partitions can be expressed as a determinant. And well, so now to get McMane's formula, all you need to do is evaluate that determinant. And in this case, that's a very easy determinant. It's a Vandermonde type determinant. So that immediately gives you McMane's formula. Now, this is not what McMane did, but he could have done it this way. So for all these other symmetry classes, we can still find determinants, but these determinants are no longer easy to evaluate. And so to come back to the completely or the totally symmetric case, for example, I've given you the determinant that needs to be computed. And you can now see that the entries of the determinants, so mostly it's a sum of two Q-binomial coefficients. But then along the main diagonal and just one diagonal below the main diagonal, you get some extra junk that doesn't look very nice. And somehow this is a difficult determinant to evaluate. And as I mentioned earlier, to date, the only way we know how to do this, or not me, but at least some people, is use clever computer algorithms that can actually do these things. So we still don't quite understand what's going on here. Okay. Well, so that's plane partitions and using determinants and non-intersecting lattice paths. It turns out that many of these problems have a close relation to representation theory. And so, for example, McMahon's original problem of just the box plane partitions, it actually turns out that it's not hard to see that really what you're looking at is a particular polynomial representation of the general linear group. And in particular, what you're computing is in fact a graded or Q dimension of a particular representation indexed by the partition where you just have B 8 times repeated, or for those who know this other language of weights, it's just a particular representation corresponding to a highest weight where omega A is just a fundamental weight of GLN, and you just take the multiple of that B times. Okay, so this is not very difficult to see that this is what you're really looking at. And then to get the product, all you need to use is just Weil's character formula, or a specialization of Weil's character formula, which just gives you a Q analog of Weil's dimension formula. Now, I mean, that was perhaps a little bit quick if you're not familiar with representation theory. If you are, then you might already have recognized that original problem to be exactly this. But the point is that there is certainly, I mean, this is quite an appealing approach in that you can understand the problem purely from the representation theoretic point of view and then get a very quick proof. And this is not just for this particular problem, but for some of these symmetry classes, something similar happens. So for example, this symmetric plane partition conjecture, which took 75 years to be proven. So this is a much harder problem, obviously. But in fact, you can recognize this as arising from a branching formula between, well, this is now the special orthogonal group and the general linear group. And this has a one-page proof. If you then recognize that you can prove that branching formula using the theory of Gelfand pairs. So this is something that I pointed out with my collaborator, Eric Rains. So again, that's quite appealing. I won't go into the details here. They're not that important. But again, we see a very close relation to representation theory. And once you understand the exact translation into representation theory, then often very neat proofs can be given. The same with another formula. So this is it's a Proctor-Stembridge formula. Again, it can be recognized as a branch, or as a special case of some branching rule. And again, you can use Gelfand pairs to settle this. Okay. So that was very quick and not a lot of detail, but the message is that there's a strong connection to representation theory. And once you understand that connection, you can give very slick proofs. So let me, and maybe I shouldn't be doing this, but let's go back to I guess this particular problem of the totally symmetric plane partitions. Obviously, what we haven't been able to do yet is, for example, translate this in a manageable problem in representation theory and then give a proof that doesn't require a computer. So that's really a challenge for everyone who's listening here to find such a proof that would be much more insightful than requiring a lot of computer algebra. But so far, we don't really know what to do here. Okay, now, in view of this connection between plane partitions and the representation theory of what are classical groups, there is a very natural question, and that's sort of where I sort of would like to talk about in my last sort of remaining 10 minutes. Are there plane partition analogues that sort of are related to affine Lie algebras, so infinite dimensional objects rather than the finite dimensional ones? Okay, so because we've seen that plane partitions, they're closely related to representation theory of classical groups, is there something going on in the affine world as well? A natural question. And so, well, this is much, much more recent, but in 1997, Gessel and Kattenthaler, they introduced indeed affine analogues of plane partitions, and they called them cylindric partitions. And here I've drawn a picture of a cylindric partition. So a cylindric partition, it's a certain type of plane partition, and I'll give you the more precise definition in a moment. And now these pictures, you can see this picture repeats itself. So essentially what I show you here in this picture is just what is the colored part is just a fundamental domain, if you wish, and then that's just repeated infinitely often. So obviously, if you try to compute the volume of this thing, given that it never stops, the volume is infinite, but you just consider the volume of a fundamental domain, like these colored boxes here, that's of course is a finite volume. So that makes perfect sense, and you can study these objects. So that is cylindric partitions. So let me give you a slightly more precise picture. So really what we do is we fix two integers, r and d, and because of its relationship with infinite dimensional Lie algebras, I'll call r the rank and d the level, because that's what they turn out to be in terms of representation theory. Well, R, you don't need representation theory, but D, that's a term coming from representation theory. And then a cylindric partition is essentially just a plane partition that's wrapped around a cylinder of circumference R squared plus D squared, well, to the power 1/2. So you see it here in the picture. And there's a given slope minus D over R. So it's really the picture on the left. And what you can do is you can cut this open, and it doesn't really matter where you cut it open. So you just have to make a choice. And so that's the picture you see on the right, but I've cut it open. So essentially, again, on top of the row that I've colored in black, that's just a repeat of the bottom row, and it goes on forever at the top, and you can do the same at the bottom, but I've only given you here this fundamental domain plus one of the additional rows on top of that. Okay, so that's a cylindric partition. And again, you just, right, you should think of these numbers as the number of cubes that you're stacking on top of this diagram. So, and this is precisely the one that corresponds to the picture that I've drawn on the previous page. Okay, so that's a cylindric partition. And typically what you do is you fix a profile. So that's these blue numbers you see on top of these rows. It's essentially this indentation. So you see that all these rows are shifted a little bit to the right relative to the previous row. And you need to do that in order to be able to wrap this. Because if you push all the rows to the left, like in an ordinary plane partition, then of course you can't put the bottom row on back to the top row because it would break the weakly decreasing conditions. So you need this sort of move, these rows need to move to the right in order to be able to sort of cycle. And so the way each of the rows is moved to the right relative to the previous row, we encode that in something we call the profile. And if you add up all these numbers in the profile, that gives you this level that I talked about earlier. And so in the example here, the profile, it's 2201. And so, of course, that means there's 4 of these. It's a composition of length 4. So the rank is 4. And if you add them all up, that gives you the level. Okay, so maybe that wasn't particularly clear, but hopefully you get some idea of what these things are about. And again, you can try to compute the generating function. And so it's a little bit more complicated now, and we can box these things. And boxing now really means that we have a limit to the height of the highest column. And well, I'm not giving you the pictures here because it's somewhat more complicated, but essentially you do exactly the same as before. So you formulate this in terms of non-intersecting lattice path, then you throw in all kinds of paths that do intersect, but they cancel out. The only real difference is, because of this cyclic property now, is that this symmetric group that we had earlier gets replaced by essentially the affine symmetric group, or really the Weil group of this type A, but now affine type A. And that means that you do not just get a determinant, because this affine Weil group has the structure of the semi-direct product of just the classical Weil group, that's just the symmetric group. That's why you see a determinant here. And then but it's a semi-direct product with a lattice, and that lattice is sort of encoded in the fact that you have these sum in front of this determinant. So the precise details are not that important. The point is that you can again use non-intersecting lattice path methods to compute the generating function. And now if you let this C, so this maximum height of the columns, go to infinity, then you get once again a very nice product formula, where now the right-hand side is expressed in terms of Jacobi theta functions. And why is this nice? Well, if you know a little bit about representation theory, you will again recognize this product on the right. So it has various interpretations. And so here are some. So up to a simple factor, which only depends on the rank, it's, for example, the graded dimension now of an irreducible representation of some highest weight module of the affine Lie algebra. So this is essentially affine SLN. And you can see the weight that is indexing this highest weight. Oops, there's certainly a typo there. There's a C1, and that next C1 should be a C2, and so on. So this profile is exactly determining the highest weight of your highest weight module. It also turns out that this product is up to a simple factor, corresponds to an actual character, not a graded dimension, but an actual character of a W algebra, where W2 corresponds to the well-known Virasoro algebra. And yet another interpretation is that, again, up to a simple factor, it corresponds to a branching function that arises if you study admissible representations, again, of affine SLN. So it's clear that these cylindric partitions, they are related, again, to representation theory. Well, that's good, but what can we do with this? Well, we can refine our earlier question. So now we have these affine analogues of plane partitions, at least in type A. Other types haven't really, they're probably out there by assuming symmetries, but no one has really studied them yet. So at the moment, we only have type A. But now we can indeed ask the question, well, can we use this? So this is sort of a new model for this representation theory. Can we use this model to actually learn something about representations? And it turns out that you can use this. So these cylindric partitions, because you can now really study or use the combinatorics of cylindric partitions to actually compute characters for these representations. And so what I'm going to do here is, again, I fix a profile. So that's all these indentations. So again, the picture you see here, that's just all these numbers in blue. And I compute the generating function of plane partitions or cylindric partitions, I should say, of fixed profile. And I keep track not just of the number of boxes, But again, I now use the maximum entry as well as a statistic. And what you can do is, so here's a picture of a cylindric partition, and you mark the boxes. I call them corner squares. So essentially that's where you have a profile so for example, you see there's one of these CIs is 0, that doesn't give rise to a corner square, but every time you have a CI that is strictly greater than 1, you have a little corner on the left and you mark those corners. And you should observe that the maximum part of that cylindric partition must occur in one of these corner squares simply because of the weakly decreasing condition on the filling of this diagram. And now you can essentially build up an inclusion-exclusion kind of procedure. So what you can do is you can remove one of these corner squares, you get a new cylindric partition, so with a different profile, but with the same level, so that sum of the CIs doesn't change. And by removing one of these boxes, corner boxes, you're removing potentially one of these sort of maximal parts of that cylindric partition. And so what that means is that you get a functional equation between the generating function of cylindric partitions of, well, different profiles, but all the levels, so all these profiles occurring in these functional equation have the same level. And so that's really, really great, because this functional equation, together with some initial conditions, uniquely determines the generating function. So all you need to do now is solve this functional equation, set z equal to 1, and this corresponds to all of the different characters, and you would have found expressions for these characters. Of course, this functional equation is not easy to solve. So for R is 1, the rank 1 case, it's trivial, and it's just integer partitions. So for R is 1, it's very easy to see that you're not doing anything more than integer partitions. And the functional equation just looks like what you see at the bottom of or near the bottom of the page. And you can immediately solve that, anyone can, with the correct initial condition, and you simply find Euler's generating function again. So that's simple. For rank 2, we also can completely solve these functional equations. It's no longer that simple, but it can be done. And so, for example, here I've given you the solution in the case of level equal to 3. So this corresponds to, so rank is 2. So this corresponds to characters of the Virasoro algebra, for example. And in this level 3 case, you essentially get, well, these Rogers-Ramanujan functions showing up. But as I mentioned earlier, solving this for general rank appears to, at the moment at least, to be too difficult. But recently I managed to conjecture the solution in the rank 3 case. And well, here is just one example of this. So the rank is 3, so you can see this profile now has 3 entries. And here's just the level in this case is, I just need to add up all of these CIs, so it would be 3k minus 2. And well, this looks like a very complicated formula on the right-hand side. It's a sum over a product of two binomial coefficients. But the point is that this expression on the right is manifestly positive. So these are manifestly positive expressions that you get for the generating function. So unfortunately, I couldn't prove this in general. I could prove it for some small values of k, but not in general. But I can prove it when z is equal to 1, and it's certainly correct. And in that case, it corresponds to characters of, for example, W3. And so you get these really nice, well, I think nice character formulas. And these sums, as I said, they are manifestly positive. And I'll end with, because this looks like a very complicated formula, so I'll end with just some simple examples of this. So for example, for level equal to 4 here, you get the sum is relatively easy, just 1 binomial coefficient. You can see that the quadratic form here of on the left hand side corresponds to, of course, the coming from the Cartan matrix of SL3. So not that surprising. And on the right hand side, you get a nice infinite product where you see sort of modulus 7 showing up. And if you bump up the level by 1, so now we see the level is 5 and you get modulus 8 and so on. And of course, now you have 2 binomial coefficients. So these things quickly become more and more complicated. Here's the next level and so on. The expression on the right already becomes quite long, and I had to use a smaller font and so on. But unfortunately, right now, I don't know what to do for arbitrary rank. So it's back to these functional equations. You can, of course, try to use your computer and see what you get. But unfortunately, if you increase both the rank and the level, you get many more profiles that are starting. So this is, of course, a coupled set of equations you get. And it's quite difficult to disentangle what goes on for each individual fixed profile. And so far, that's where things stand. And that's probably where I should stop. So thanks very much.
Right, thanks very much, Ole. So let me applaud on behalf of everyone here. Thanks for a clear talk. So people can ask questions through the Q&A function. Please don't use chat, but use the Q&A at the bottom of your Zoom screen. Ole, I don't know if you can read the questions, but
not yet. I'm trying to.
I'll read one. The first one. I understand that there is some close relation between plane partitions and enumerative geometry. Can you say a few words about any known roles of cylindric partitions in enumerative geometry?
I believe, I'm not sure they have shown up in enumerative geometry, the cylindric partitions. The literature on cylindric partitions is surprisingly small still. So there's still a lot to be done. And I don't think they have shown up in that context just yet. But of course, I would say the fact that they clearly have the connection with the representation theory of infinite dimensional Lie algebras. So surely, because of that connection, you can push this a lot further. Whether you can understand these things in terms of enumerative geometry, I do not know. But I'm not aware of any results along these lines, so unfortunately.
Okay. So there's two related questions, whether there are any closed form expressions for higher dimensional partitions, I guess.
No, so as I already indicated at the start, we believe that, so the first answer to that question is no, there are no closed form expressions. Do we believe that maybe one day people will find it? And I think the belief generally is also no. So one of the reasons, for example, that you get all these really nice formulas in the case of plane partitions is the connection to representation theory, because all these infinite products that we see, they all come in they're all dimension formulas or Q dimension formulas, or some people who take the point of view of integrable systems, there's Yang-Baxter equations in the background and so on. So there's a lot of integrability here. Once you go beyond 2 dimensions, we believe that all of these connections are lost. And so there's no reason to expect anything nice to happen. And indeed, we haven't found anything nice to happen. So people have sort of lost the belief that, well, one day someone will find a connection with representation theory or integrable systems, and suddenly things will become nice. So I think we have very little hope there.
So that answers the second question by the same person, whether there is a representation theoretic interpretation for higher dimensional partitions. I guess the answer is no.
So unfortunately not.
Yeah.
Yes.
Another question, is there a connection to gap probability distributions? For example, to the Q-Han orthogonal polynomial ensemble?
Well, there. I mean, it's certainly not true that there's no connection to orthogonal polynomials and plane partitions, but I don't think orthogonal polynomials so far have really played a major part in making progress on plane partitions. But some of these problems you can express in terms of orthogonal polynomials. But I'm not really aware of something that is really deep and meaningful. So that's maybe not a very satisfactory answer. Yeah, I'm not really sure what to say here. I mean, there's a lot of special functions going on, and in some of these sort of, if you do some of these calculations, you can certainly use orthogonal polynomials sort of in the ASCII or the QASCII scheme to answer some questions, but I'm not really sure what that means actually, so.
Okay, another question then, is there an analog of T-core partitions for plane partitions?
An analog of T-core partitions for plane partitions? No, there is not. No, there is not. Again, no. Yeah, that's an interesting question. Of course, the T-cores and T-quotients and these kind of things, of course, they first really came from the representation theory. Essentially, if you do representation theory or modular representation theory of the symmetric group and so on. So here you could try to define something that is analogous to that. It would maybe be somewhat artificial. Yeah, but you could, of course, take a plane partition and again say, rather than removing ribbons, you're removing whatever sort of three-dimensional shapes such that of a given number of boxes. And then what you remove, it should still be a plane partition, and then keep going and you would get something that is a core. So you could define something like that. But the question is, of course, is that interesting? Is there a good reason to define that? So certainly no one has ever done that. And I doubt that it would lead to something that is really meaningful. Anyway, it's not out there, that's for sure.
So I have a question as well. Does the affine direction allow you to introduce an extra parameter with the new statistics? Like for example, with integrable systems, you would have a seam when you put a system on a cylinder.
Well, so the answer is yes. There's many additional parameters that you can introduce, and so for example, I didn't. So where do I start with my cylindric partition? So certainly what Gesser and Kattenthaler introduced was way more general than the picture I'm showing here. And in the general case, you have heaps of parameters, and whether you would that would correspond to something that would be a seam, say in integrable systems, I'm not exactly sure, but there's a lot of statistics that are naturally attached to these objects, and there's a lot of additional conditions. So you can really put conditions on individual rows and columns and so on, and they can still compute generating functions in terms of determinants. And so, for example, this generating function that I've shown you here, it's a little bit different to what I showed earlier, because in the earlier non-intersecting lattice path case, I showed a determinant that contained a Q-binomial coefficient. Here, that's no longer the case. That's because I've already sort of taken a limit of several other parameters that you can easily keep track of, and then you would actually get a determinant of Q-binomial coefficients containing many additional extra parameters. So there's a great deal of freedom of what you can do, and there's a lot of meaningful statistics attached to this.
Okay, yeah, I guess I was asking specifically about the affine direction.
Yeah, in the affine, well, Well, but this is affine, right? So even in the affine direction, this is the affine direction. So there's a lot of additional parameters that you keep track of. If you really want to end up with things that correspond to characters of well, all of these, where did I state that? All of this kind of stuff, you essentially need to get rid of almost all of these additional parameters, because the only thing that really sort of encodes things is the highest weight of the corresponding highest weight representation. And that's already encoded by this profile. So everything you have on top of what is the profile doesn't have a natural interpretation in terms of representation theory. And so it's much less likely that something nice will still happen. But having said that, for example, keeping track of this max statistic here, which we don't know what it means in terms of the representation theory, it certainly is crucial to set up, for example, these functional equations. And so having additional statistics which naturally arise in the context of these. So it's a really good model to have for your representation theory, because there are so many other natural statistics, and some of them are really useful in doing calculations. I'm not sure they're useful, they really mean something in terms of the actual representation theory itself, but they're just a useful tool. So it certainly helps. I mean, we know this in mathematics throughout, of course. The more variables you have, of course, usually the more easy it is to do actual calculations. So these additional statistics are certainly helpful, but I don't think they necessarily mean anything. Okay.
Here's another question. Do you have any idea about what the untwisted affine type C analog of the cylindric plane partitions are? Like some,
well, I mean,
some kind of
in fact, I've had some discussions with Christian Kattenthaler about this, because I mean, they make some suggestion. They speculate in their original paper about what type C would be, which doesn't seem to be the natural, because you could simply say, well, all you need to do, so let's go back to a picture, is take a picture that is symmetric. Because that's in the classical case, if you take symmetric plane partitions, well, it doesn't give you type C, it gives you type B, and then you need to do some additional conditions along the main diagonal, and you would get type C. So certainly these other types are there. Here, of course, it's not entirely clear. You can certainly take a picture like this and assume symmetry, so that this whole picture would symmetric upon reflection, which is not the type C that they speculate about in their paper. I asked Christian if anyone has, right, it's been more than 20 years since they introduced these things, if anyone has studied the symmetry classes for these. And so far, no one has. So I don't know why. I mean, it's pretty clear there must be a type C, type B, and whether we get twisted cases, well, that's an even more speculative question, but it's pretty clear that we should not just be getting type A. In the classical case, we get all these other types, so we should be getting them in the cylindric case, but no one's done it. Somewhat surprising. So yeah, so you can speculate what exactly the right definition is to get type C or to get type B. As I said, Christian and I have slightly different ideas about what it should be, but no one's done it.
Okay, so we went through all the questions. I think this is a good point then to stop and thank Ole again for a wonderful talk. So I'll clap on behalf of everyone here. Thanks very much, Ole. And thanks everyone for attending. Don't forget, there's a new Matrix Online seminar next month when we have Avi Richardson, Abel Prize winner this year from the IAS. So I hope to see you then. Goodbye, everyone.
Thank you.